Welcome to Part 2 of Module 8. The learning outcomes for Part 2 of Module 8 are: identify electrolytes and non-electrolytes, identify important strong and weak acids, identify important strong and weak bases, and solve questions relating to pH. Electrolytes are compounds that dissociate in water and form cations and anions, and thus they are able to conduct electricity. On the other hand, non-electrolytes are substances whose aqueous solutions are non-conductors. For example, if we set up a conductivity apparatus and try 3 different solutions, pure water does not light up the bulb as it is not a good conductor. The second product is sugar, and again it does not conduct electricity because it is a non-electrolyte. The last one is sodium chloride, and it lights the bulb because it is a strong electrolyte. It is the movement of ions that conduct electricity in water. Acids, bases and salts are electrolytes because they produce ions in water when they dissolve. This table gives some examples of electrolytes and non-electrolytes. Salts dissociate into cations and anions when they dissolve in water. For example, sodium chloride dissociates into the sodium cation and a chloride anion. When sodium chloride dissolves in water, each Na plus and Cl minus ion becomes surrounded by water molecules. The negative end of the water dipole is attracted to the sodium ion, and the positive end is attracted to the chloride ion. Ionization is the formation of ions, and it is the result of the chemical reaction with water. Acids ionize in water, producing hydronium ions and anions. For example, HCl plus H2O forms H3O plus Cl minus. Because HCl is a strong acid, the reaction happens in the forward direction only. Let's look at another example. H3PO4 plus H2O gives H3O plus H2PO4 minus. Because H3PO4 is a weak acid, then the reaction happens in both directions. Weak bases also ionize in water, producing hydroxide ions and cations. For example, NH3 plus H2O gives OH minus plus NH4 plus. Which of the following compounds will not dissociate when placed in water? The answer should be A, methanol, because it is a non-electrolyte. B is a strong acid, and it easily dissociates in water. C is a salt, and it also dissociates in water. And D is also an acid, and it will dissociate in water. A solution is tested with the conductivity apparatus and gave a positive reading. Which of the following is likely? The answer should be C, because calcium chloride is a salt and it ionizes in water. Strong electrolytes are essentially 100% ionized in water, for example HCl. Weak electrolytes are much less ionized, for example acetic acid. Acids and bases that are weak electrolytes are called weak acids and weak bases. Acids and bases that are strong electrolytes are called strong acids and strong bases. In this picture we have 2 beakers that contain 2 different acids. HCl is completely dissociated, or we can say it is 100% ionized. The second beaker contains acetic acid, which is a weak acid, and you can see that only one molecule dissociated, and the remaining are still in the molecular form. This table presents some of the important strong acids and bases. It also shows weak acids and bases. Strong acids include H2SO4, HNO3, HCl, HBr, and HClO4. Strong bases include NaOH, KOH, CaOH2, and BaOH2. Some of the weaker acids include H2CO3 and H3, and the only weak base that you need to learn is NH3. For weak electrolytes, we use double arrows to indicate weak ionization. For instance, we use double arrows with the following two acids as they are weak acids. Salts dissociate into at least two ions. For instance, a 1 molar solution of sodium chloride produces a 2 molar solution of ions according to the following reaction. 1 mole of NaCl gives 1 mole of sodium ions plus 1 mole of chloride ions. A 1 molar solution of calcium chloride produces a 3 molar solution of ions according to the following reaction. 1 mole of calcium chloride gives 1 mole of Ca2 plus ions plus 2 moles of Cl minus ions. Let's practice an example. What is the molarity of each ion in a solution of 0.07 molar AlCl3? First, we need to write the equation. AlCl3 gives Al3 plus 3Cl minus. The ratio is 1:1:3. So the molarity of each constituent is AlCl3 is 0.07 molar, Al3 plus 0.07 molar, and Cl minus 3 times 0.07 molar gives 0.21 molar. What is the concentration of chloride ions in a 2 molar solution of calcium chloride? The answer should be D. What is the molarity of each ion in a solution of 2 molar sodium chloride or 0.4 molar potassium sulfate? Let's assume complete dissociation. The ratio is 1:1 in the first salt, so we expect to get 2 molar Na plus ions and 2 molar Cl minus ions. In the second compound, the ratio is 1:2:1, thus we expect to get 0.8 molar for K plus and 0.4 molar for SO4 2 minus. Pure water goes through auto-ionization, meaning it starts ionizing with itself. This is shown as H2O plus H2O converts to H3O plus OH minus. At 25 degrees Celsius, if we measure the concentration of those ions, we find it as 10 to the negative 7 molar. So, if we multiply those together, we get 10 to the negative 14. In acidic solutions, the H3O plus concentration is greater than the OH minus concentration. And in basic solutions, the inverse is true. However, it is important to note that when the concentration of one ion decreases, the other will increase, and the total concentration of the two ions remains the same at 10 to the minus 14. The square brackets are used as an abbreviation to indicate the molar concentration of those ions. Because the concentrations of these ions is very small, we use the pH scale as a convenient measure to make numbers easier to work with. This pH scale is a logarithmic calculation of the concentrations of ions. A solution with a high concentration of protons and a low hydroxide concentration is acidic with a pH of less than 7. A solution with equal concentrations of hydrogen ions and hydroxide ions is neutral, where the pH is equal to 7. A solution with a high concentration of hydroxide ions and a low concentration of hydrogen ions is basic, and its pH will be greater than 7. The table on the right shows some pH values for common solutions. For example, water at 25 degrees Celsius is neutral and has a pH of 7. The table on the left shows the relationship between the pH and the hydrogen ion concentration. As previously mentioned, the pH is a logarithmic scale, so a change of 1 pH unit reflects a tenfold increase or decrease in proton concentration. pH is calculated using the formula, the negative log of hydrogen ion concentration. A logarithmic scale is a useful way to represent information, especially when there are exponential changes in the magnitude of the numbers. Because we are dealing with very small number of hydrogen and hydroxide ions, it is appropriate to use the logarithmic function to the base of 10 to make numbers easier for calculations and expressions. The following graph shows the benefit of using the logarithmic scale to report the pH. It's good if you have your calculator handy for this part of the module, as it is very important to practice calculating the pH using the log function on your calculator. You also need to practice calculating the inverse of log when you are asked to calculate the hydrogen ion concentration from the pH. Don't use your mobile phone, as you will not be allowed to use it during exams. To calculate the pH value, you need to use the log function in your calculator. Every scientific calculator should have a log button that looks similar to this one. The log to the base 10 of a number is simply the power to which 10 must be raised to give that number. For example, log of 100 is equal to 2. On your calculator, you should get something like this picture. For instance, log of 1000 is 3, and so on. The log button in your calculator is for base 10, and we will only use this base in this course. So to make things easier, we can write the log without worrying about writing the base. We discussed previously that in pure water, the concentration of hydrogen ions is equal to 10 to the minus 7 molar, so the pH is 7. This point is considered the neutral point on the pH scale. From the following diagram, you can see that acid solutions have a pH lower than 7, which reflects the fact that there are more protons than hydroxide ions in the solution. On the other hand, basic solutions have a pH greater than 7, which reflects the fact that there are more hydroxide ions than protons in the solution. Let's see an example. How many times more acidic is a solution with a pH of 3 than a solution with a pH of 5? The answer should be C, 100 times. Remember that pH is a logarithmic scale, so 2 points change in the pH means that you have 10 times 10-fold change in proton concentration, so that's 100 times different. You can also calculate the answer using the following analogy. pH 3 means the concentration of protons is equal to 10 to the minus 3. pH 5 means the concentration of protons is equal to 10 to the minus 5. So if you divide the first number by the second, you get 100. Let's practice another example. Calculate the pH of a solution containing 0.015 molar hydrogen ions. We use the formula pH equals the negative log of 0.015, which if we put into our calculator will give 1.82. The calculation should look like the picture on your calculator. Now if you check the answer on the calculator, you see many decimal places. So what is the rule of significant figures in the case of logarithms? As a general rule, we include the same number of decimal places as the number of significant figures that we started with. So the question included 2 significant figures, then we should include 2 decimal places in the answer. In some cases, we know the pH of a solution and we are required to calculate the hydrogen ion concentration. To do that, we need to do the reverse step and use the formula hydrogen ion concentration is equal to 10 to the minus pH, or take the inverse of the log. For example, calculate the H plus concentration of a solution with a pH of 3.5. Hydrogen ion concentration is equal to 10 to the minus 3.5, or inverse log minus 3.5 equals 3.16 times 10 to the minus 4 molar. If you look at your calculator, you should get a similar picture. If we apply the rule of significant figures, we have 1 decimal place in the pH number, so we should have 1 significant figure. When we calculate the pH, if the first number is exactly 1, then the exponential is your pH. For example, hydrogen ion molarity is 1 times 10 to the minus 5, then the pH is 5. When the number is not 1, then we need to use our calculator to do the calculation. For example, 2 times 10 to the minus 5, the pH is equal to 4.7. Let's look at some more examples. What is the pH of a 0.02 molar hydrochloric acid solution? Remember that HCl is a strong acid, so it completely dissociates. Therefore, the concentration of hydrogen ions is equal to the concentration of the hydrochloric acid, as the ratio is 1:1. Thus, the pH is equal to the negative log of 0.02, giving 1.7. So the correct answer should be C. What is the pH of a solution of sodium hydroxide that has a hydronium ion concentration of 2.5 times 10 to the minus 11 molar? The correct answer should be D. This is the end of part 2. Please proceed to part 3, where we will discuss the titration and neutralization concepts.